In this video, we're going to discuss a method that can be used to solve all sorts of linear systems, and this method is called the method of weighted residuals. So again, a very generic scheme where we're going to be looking at equations of the following form, namely L U equal to V. What do I mean by these different terms here? So V is the excitation of the problem. So it's basically a source driving our physical phenomenon, if you want. And this is going to be a known thing in our setup. So we know the source, we know how we excite the system. That excitation will result in some sort of response, which is U, and U is our unknown response, our unknown solution to the equation. That's precisely what we want to figure out. We want to figure out how our system responds to the excitation. And then the physics of the problem, they're basically encoded into this thing L here, which is a linear operator. So this thing could either be a differential operator or an integral operator that describes the physics of the problem. Very abstract, very generic formalism. The question is, can you make this a little bit more concrete? For example, pause the video and see how you can cast the Helmholtz equation in this particular formalism over here. So the Helmholtz equation, as you know, this is the Laplacian of the field psi plus k squared psi equal to 0. So this is the form of the Helmholtz equation that we've studied. So this means that in our case, there is no right-hand side, there is no excitation in this particular form that we've studied. So V is equal to 0. Our unknown, of course, in our case, we've denoted that by psi, but that's just notation. But the question is, what is the linear operator in this case, operating on our function psi, giving us an excitation of 0? Well, purely symbolically, we can write this as an operator which consists of the Laplacian operator plus k squared here. And this is just a more abstract way of writing down what we have up here. So if you just expand this as a linear function, we have Laplacian operating upon psi plus multiplication by k squared operating upon psi, giving us indeed this equation over here. Okay. So this gives you a feeling for the types of problems that we're going to study here. So our question is figuring out what the unknown result of the excitation U is. So how are we going to do that in this method? Well, we are going to construct an approximation, U tilde. And to make notation a little bit easier, I'm just going to look at the one-dimensional case here. And I'm going to construct this unknown function as a sum of known basis functions. So I have a set of basis functions, bi here, and then I multiply them by unknown expansion coefficients, ui, and then I sum from 1 to n. So very important here is that b is known. These are known basis functions. We choose them however we want, for example, to incorporate some aspects of the physics of our problem so that we have a much more efficient representation. U, this is the unknown set of numbers that we're interested in. And then also interesting to note is that we truncate the series at a finite number of summation terms here so that we can tackle it using numerical methods on a computer. So this is the approximation U tilde that we are constructing. Now the question is, pause the video and think philosophically about the question, what do we really want from our approximation U tilde, and how will you express that mathematically? And does this actually help you? So very abstract, generic questions, but perhaps think about this for a while. So, in essence, what you want is that this approximation U tilde resembles the real unknown function U as well as possible, right? That's basically the whole goal of our procedure here. This means that if you look at the difference between the approximation U and the real solution, the approximation U tilde and the real solution U, that you would like to have some sort of metric which is related to this difference and which then minimizes this difference here. The issue here is if you want to do this directly, you basically do not know what this U is, because remember, this is the unknown true solution. So if you construct a certain approximation U tilde, you cannot really figure out how close that approximation u tilde is to the true solution u, simply because you do not know u at this stage. So this seems like a logical start, but we're still stuck at the moment because we have a target which is unknown. We really don't know what we're shooting for. So that's a problem. However, there's something we can do to bring us out of this conundrum, and that is trying to apply our linear operator L on both of these terms here. So pause the video, do exactly that, and see if now you've become unstuck. So what happens if we apply our operator L? Then we have L u tilde minus L u. And now we're in a lucky situation because we do not know what u is, but we do know what L operating on u is, because that's exactly our source V. This is the problem that we're trying to solve. So now we're in a different situation. Although we do not know the difference between u tilde and u, we can evaluate the difference if we propose a certain set of coefficients u. We can evaluate the difference between L of u tilde and V. So now we do have a concrete goal to shoot to, namely to minimize this difference between these two quantities. And since this is so important, this has a name of its own, and this is called the residual of the solution. And again, remember, since all of these guys, u tilde and v, they're function of x, the residual here is also a function of x. So if I write down explicitly what u tilde was, remember u tilde is the sum I going from 1 to n unknown expansion coefficients ui, known basis functions bi of x minus v of x. So this is our residual. So now the problem is reduced to finding our unknown expansion coefficients ui in such a way that this residual here is made as small as possible. But there's different ways you could go about this. Pause the video and see if you can propose a number of different approaches. Now, the ideal situation would obviously be that our residual r of x is equal to 0 for all possible values of x that you're interested in, right? That would be fantastic. However, this is obviously out of reach because we have only a finite number of terms to approximate our approximate solution, so we will never be able to satisfy this ideal here. So we have to lower our expectations a little bit. And one thing you could do, for example, is say, okay, it will not be possible to make r of x identically equal to 0, but I could sort of try to make it 0 on average. I could look, for example, at the energy in my error residual and try to minimize this thing. That would be a valid approach, right? Another thing you could do is, okay, perhaps it will not be possible to make r of x equal to 0 everywhere, but I have a set of points where I really care about, and perhaps what I would want is that at these specific points rj, my residual is actually equal to 0, and then I don't care about what's happening outside. So if I have n points here, then perhaps I can make this residual equal to 0 for those specific n points. Again, another very valid strategy to try and find the u values that sort of like reach for a certain criterion over here. However, what I would also like to introduce now is yet a different way of trying to find these unknown expansion coefficients u. And this way will at first seem very artificial and very generic, but later on we will be seeing that these two guys here are basically special cases of the more generic approach that I'm going to introduce now. So what is this generic approach? I'm going to introduce a new set of functions, namely the so-called weighting or test functions. So weighting or test functions. And again, I can pick them however I want to choose. I have full freedom of figuring out what choice I would like to make for these W functions, for these test functions. And I'm also going to define a scalar product between two functions, f of x, g of x. And again, however, I would want to define that scalar product, for example, by defining them as having the product of f and g. If I want, I can introduce another weighting function in this, this scalar product. which is not to be confused by the set of weighting functions that I have over here. This is just another weighting function that I introduce in my definition of scalar product, which I can do if I want to, but I'm not obliged. So again, I can pick this scalar product and the set of weighting functions in whatever way that seems interesting and plausible to me. Okay. So now what I'm going to ask is, I'm not going to say that my residual is equal to 0 everywhere for all possible values of x. No, what I'm going to ask is that my residual, r of x, and if I take the scalar products with a certain weighting function, wj, that this scalar product is 0. And I do this for all possible values of j. So I'm basically demanding that my residual is orthogonal to all of my test functions, to all of my weighting functions. So I'm sort of like weighting my residual. So this is where the method gets its name, the method of weighted residuals. Okay. So now what I suggest you do is pause the video and see if you can write this thing as a linear system, as a matrix problem, and that will obviously be the way forward to solve this thing numerically. Okay, so if I make use of my definition of my residual, well, the residual, that was my operator L operating on the sum of ui bi. Okay, so I'm not going to write down again that this is a function of x in this case. And then I subtract my excitation v, and then I take the scalar product with wj, and this thing should be 0. And I can write this down n times. If I bring the excitation stuff to the right-hand side, I can write the following. So L operating on the sum, I weigh this, and then on the right-hand side, I have the weighted version of excitation V. Don't forget, our operator L is a linear operator. So if I operate with L on the linear combination, that's the same thing as that linear combination of stuff with L being operated on. So I can write this as U tilde here. And now L operating on BI. Okay. WJ. And then here I have VWJ. That was just exploiting the linearity of the operator. But don't forget, the scalar product is linear as well. So a scalar product of a linear combination is the linear combination of the scalar products. So I can bring this linear combination outside of my scalar product sign. So I have a sum over I ui, and then I have the scalar products LBI WJ, and then for the right hand side I have VWJ. Okay. And again for j going from 1 to n. So I have n equations for n unknowns ui, and all of these guys are numbers which I can evaluate. So I'm looking at a linear system here with n equations and n unknowns. I can write this a little bit more compact using definitions of certain matrices. So if I want to do that, then I could, for example, try and first of all write down what you have for j equal to 1. So if I explicitly write down this summation here for j equal to 1, but I want to do that in a way that results from, for example, a multiplication of a matrix by a vector, then as a vector, I could have a vector where all of the unknown expansion coefficients are its elements over here. Okay, so let's see what happens. So I have I in the summation running from 1 to n. So I have a term for u1, I have a term involving u2 all the way up to I equal to n, so term equal to un. Now, if I write this thing down where j is equal to 1, what is then the coefficient of u1? Well, this is going to be LB1W1, right? And then if I have the next one, this is going to be LB2W1. Again, W1, because we have a fixed j equal to 1. This goes all the way on to L, and then I have BNW1. Okay, And then for the right hand side, I had for the first equation, I have VW1. I can keep on playing that game, writing down other equations for other values of j. So for example, if I have j equal to n, then what I have here in the lower left, I have LB1 again for the first equation. And then here, W is the stuff that's related to j. So this time j is equal to n. Now I have Wn over here. And here I have LBN Wn. Okay, and then my right hand side here is VWN. So the stuff in this matrix is all known. I can evaluate this thing. I know how I've chosen my basis functions, my test functions. So I've defined my scalar product, so I can evaluate all of the elements in that matrix. I can do the same thing for my known excitation and the weighted versions here in the right hand side. So this is in essence a linear algebra problem where I have a matrix L here, column vector U, which is unknown, and then a right-hand side matrix V. So it's pretty obvious that U is this vector and that V is that vector. What about the definition of this system matrix L here? Well, if you take a look at what's going on, if you look at the ijth element of that matrix, so if you look, so I is obviously the row index, so I runs like this. Now what happens if you're looking at a certain row? Remember, each row is what we got when we fixed j to a certain value. So this is related to the index here of w. So if you're looking at the ith row of this matrix, this basically means in the scalar product, we're looking at multiplication with wi. And then the column thing, if you look at how the columns evolve in different columns, you're looking at different indices for b. So here we have L operating on bj. So it's a little bit unfortunate that the sequence of I and j is exchanged in this way, but that's no big deal, obviously. The important part is that we went from an operator equation where we had an operator operating on a function resulting in another function, that we've sort of projected this equation into a linear algebra system where now we have a finite number of unknowns. Okay. Now, then I have a linear system which you can solve with your favorite numerical algebra package, and then you have your result. Before we wrap up, some other names for this method of weighted residuals are the method of moments, that's another name for this method, or also the generalized Galerkin method, if you want to be a little bit more, have a little bit more variety in ways of referring to this very generic and very powerful method. In the next video, I will show how different choices of the weighting functions and the basis functions result in different flavors of this method. For example, trying to figure out that R is equal to 0 for certain values of X, or trying to minimize the energy in the residual. But that's for the next video.